Okay, guys, welcome back. Sorry, I'm running just a few minutes behind today. A lot of the class elected to postpone exam 2, so I was making sure everybody was set up and moving happily through that in the makeup session. I did think that more than 3 of you took the test on Friday, so hopefully a few more folks join us here today. But yeah, so today's actually a pretty gentle day. I'm expecting relatively low attendance because of the makeup test. So what we're going to do today is introduce the kind of main goals and ideas for the last big chunk of this class. So the last third of this class isn't about derivatives. It's about the other thing that we do in calculus, which is called an integral. And that happens to be related to something called an antiderivative. So today I'm going to kind of introduce and motivate the standard geometry problem that led to the discovery of the new kind of calculus that we're going to be doing in the last third of this course. And you'll be doing pretty much through all of Calc 2.
Quick question. Are there any like extra credit opportunities or anything like that?
Not really, no. So the final exam can replace your lowest midterm, and that's sort of the biggest hammer we have in that direction. But there isn't any like straight up extra credit.
Okay, thank you.
So let me throw out the title card here. This is MAC2311, section 004, which is a Calc 1 class. And the date today is the 21st of March, 2022. Today we're going to introduce what's called integral calculus. So you can sort of think of calculus as being split into 2 branches. There's differential calculus and there's integral calculus. Today we meet the second half, and we're going to do this via this problem of areas and distances. And that's actually the title of the section here, is areas and distances, which is section 5.1. From a mathematical standpoint, the main goal is given sort of nice enough function f on an interval AB, can we find the area bounded by f and the x-axis or horizontal axis? What I mean by nice enough, turns out the function doesn't have to be differentiable. It doesn't even have to be continuous, but it has to be like piecewise continuous. So if I draw just some sort of generic function in here, the idea is that maybe A is over here, maybe B is over here. And I would like to find this area, the area bounded by f on that interval. I'm going to get in the habit here of shading areas in pencil. So this is sort of the game. This is x. It's the graph y equals f of x. Now we call this section areas and distances because in the kind of physics interpretation, if this curve is your velocity function and the horizontal axis is measuring time, then there's a physical interpretation of this area as a displacement or distance traveled. But we'll get to that in just a minute. The main tool that we're going to use to get started here is very, very simple. Instead of trying to calculate the exact area, we're going to drop in a bunch of rectangles and find the areas of those. The main tool we use at first here, later I will develop a better tool for this, is called a Riemann. This is the name of a man, R-I-E-M-A-N-N, Riemann sum. If you've ever heard of the Riemann hypothesis, it's a very famous problem in mathematics that is open to this day, still unsolved, worth $1 million if you can solve this math problem. It's named after the same guy. Okay. So what is a Riemann sum? It's basically adding up the area of a bunch of rectangles. It's the thing a 5-year-old would do if you ask them to try and find this area, right? You draw in a bunch of rectangles, you can find the area of rectangles, so you can add those up and get at least a good approximation to the total area. Riemann sums are usually expressed in something called sigma or summation notation. So first, a review of that notation. So this symbol I've just drawn here kind of looks like a big weird E. That's the Greek letter sigma. That is a capital Greek sigma from the Greek alphabet. And generally it stands for the word sum. As in to add this thing up. So sigma with some stuff is equal to what you get when you add up all the stuff. And usually we index these sums with some variables, some symbols, usually like an N or an I or a K. So I'm going to show you some examples, and then we're going to define the Riemann sum. I'll show you the geometry of the Riemann sum. There's actually several Riemann sums, and we'll use them to do some computations. After we've done that, we'll look at a couple applications from the world of physics. But yeah, in order to get started here, you got to be comfy with this sigma summation notation. That will also play a big role in Calc 2, not just talking about areas, but more importantly, they're talking about these things called infinite series. So anyway, here's some examples where we can calculate some sums using the sigma notation. So we're just going to calculate each of these. All right, just to see how we're feeling about the notation. So remember what the capital sigma here means is add some stuff up. So we're going to have a big long addition problem over here. The stuff that we're adding up is the thing to the right of the sigma. And these numbers down here, the little n equals 1 and the 4 up here, tell you what range of n you're going to add up over. So I'm going to be adding up n squared as n runs from 1 to 4. That's how you read this. So this is the sum from n equals 1 to 4 of n squared. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared. That's the idea. And this is 1 plus 4 is 5 plus 9 is 14 plus 16 is 30. So this just spits out a number. The next one is the sum from k equals 1 to 3 of 1 over k. So that's 1 over 1 plus 1 over 2 plus 1 over 3. Or 1 plus 1/2 plus 1/3. So 1 plus 1/2, that's 3 halves. And then 3 halves, so let's see, this is 3 halves plus 1/3. And if we have a common denominator between these two, if I multiply this by 3 over 3, this becomes 9/6. If I multiply this by 2 over 2, this becomes 2/6. So 9/6 plus 2/6, that's 11/6. And then the last guy is the sum from I equals 1 to 5 of 2i plus 1. So that's 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus 2 times 4 plus 1. I'm almost out of space. Plus 2 times 5 plus 1. So that's 3 plus 5 plus 7 plus 9 plus 11, which is 8 plus 7 is 15 plus 9 is 24 plus 11 is 35. So this is the notation that we use to express big addition problems. Because we're going to, with Riemann sums, be adding up the areas of a bunch of rectangles, we'll end up writing one of these capital sigmas here, and then some expression that represents the area of each rectangle. Before I get into that, I want to show you some rules for the sigma operator. And I'm going to state it like this. Sigma is a linear operator. And those are some words that we've heard before, but not in a while. So the last time we heard the words linear operator was when we first introduced the derivative. The derivative is a linear operator. And what that meant is you could split it up over addition, right? Like f plus g all primed is f prime plus g primed. And you can pop out constants. So like c times f all primed is c times f primed. Sigma works the same way. So what I mean by that is if you have sigma, say, I from, I don't know, 1 to n of two things in here, say a sub I plus b sub I, which would be like a1 plus b1 plus A2 plus B2 plus A3 plus B3. This is equal to sigma I from 1 to n of AI plus sigma I from 1 to n of BI. So you can split up the sigma over addition. And the other one, if you have sigma I from 1 to n of some constant times AI, this constant can pop up. That's C times sigma I from 1 to n of AI. So what does that mean? It means that I can compute sums, say like part C here. Instead of straight up writing this out, I could have split it up as sigma 2i plus sigma of 1, and then computed each of those on their own. So let me show you a quick example here how we can make use of this. Maybe I'd like to compute sigma I from 1 to 4 of, how about 3 times 2 to the I plus I. What the rule above tells us is that I can first write this as sigma I from 1 to 4 of 3 times 2 to the I plus sigma I from 1 to 4 of I itself. That's using the addition rule. And then using the rule for constant multiples, I can pop the 3 out of the first sum. So that'd be 3 times the sum from I equals 1 to 4 of 2 to the I plus sum I from 1 to 4 of I itself. And then I can compute each of these. Each of these is a little bit simpler to do on their own than if I had to do it all at once together. Same sort of ethos as doing derivatives one part at a time. This 3 is going to be distributed across every term here because of course it was originally included in every term here. So I open up a parentheses and then 2 to the I summed from 1 to 4. Oh, okay, Marvin. Yeah, that's fine. That's fine. So here, 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 is this part here. And then the sum from 1 to 4 of I itself is 1 plus 2 plus 3 plus 4. So this is going to be 3 times 2 plus 4 plus 8 plus 16 plus what I have here. I'll just write it like this. We'll do those 2 steps at once. Okay, so 2 plus 4 is 6. 6 plus 8 is 14. 14 plus 16 is 30. This is 3 times, and like this, 3 times 30 plus 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. So we get, oh, this is unplanned. Nice coincidence. We get 90 plus 10, 100. So that's sort of how you use that rule to make your life easier when working with the sigma operator. the in-between step that I'm covering there is this. There's one last thing about the sigma operator before I jump into the geometry of the areas, and that's some special formulas. So one of the reasons these two rules are so useful, like you saw here, is it allows me to take a kind of complicated sum and split it up into simpler sums. I can make my life even easier still if I had a nice formula for simple sums like these, or for simple sums like these. I'm going to give you a few such formulas, not all of them that are known. Of course, there's many such formulas. Summation formula are kind of a big deal. But a few standard ones that we will use include some summation formula. One of these has a very cute story behind it. I'll begin with a boring one. Sigma I from 1 to n of some constant c. What this is c plus c plus c, just n times. So if I add a number to itself n times, I'm going to get n times c. This next one is the one with the cute story. Have you guys ever heard of the mathematician Gauss, Carl Friedrich Gauss? He shows up in physics a lot too. Well, Gauss was a very precocious young man, like as a little kid, talking like 7 years old. So like second grade Gauss, baby Gauss. Baby Gauss was very precocious, always shouting out answers in class, never letting the other kids talk, and eventually his teacher got annoyed with him. So one day during math class, Baby Gauss's teacher said, "Baby Gauss, please shut the fuck up. I want you to go add all the numbers from 1 to 100, 1 plus 2 plus 3, all the way out to 100. And it took Gauss all of like 10 seconds to come back with the answer. And he says, here's how I do it, right? This is 1 plus 2 plus 3, all the way out to, let's see, the second to last term would be n minus 1, and the very last term would be n. It's like if this was the sum from I equals 1 to 10, this would be 1 plus 2 plus 3 up to 10. Baby Gauss said, I take the first term and the last term, and I add those together. So, okay, 1 plus n, that's n plus 1. Then I take the second term and the second to last term, and I add those together. Okay, 2 plus n minus 1, that's also n plus 1. If I take the third term and the third from last term, that would be 3 plus n minus 2. That's also n plus 1. So this is really a bunch of, by like taking the outer pieces and adding them up, those all add up to n plus 1, each one of them. How many of them are there? Well, if there's n terms in the sum, then there's half of those, or n over 2 pairs. So Baby Gauss said, this has to be n times n plus 1 over 2, because it's n plus 1 times n over 2. I always thought that was a cute story.
Would the bottom term still be 2 if I was not 1?
No. So if you change this starting index from 1 to something else, this formula does not work. And that's true for this one also.
Okay.
Yeah, so all of these do require that the starting index is 1. The first one you could modify pretty easily. If this one started at like 2 or 3, then you'd have like n minus 1 or n minus 2 copies of C. This one you'd have to be a little more careful with to modify like that. But yeah, we do require that these start at 1. If you change that, we get into trouble. Other fun question, while we're there asking fun questions about this sum, we said that there should be n over 2 copies of n plus 1. That's how Gauss did it, right? Like this guy and this guy is n plus 1, this guy and this guy is n plus 1. Well, that really only works if n is even, right? So does this formula still work if n is odd? The answer there is yes. And if you can explain why, then you'll have a nice deep understanding of this formula. It's a good thing to play with. So we've got the sum of a constant, the sum of the first n integers, the sum of the first n squares. This is like 1 squared plus 2 squared plus 3 squared. The second to last term would be n minus 1 squared, and the last term would be n squared. This turns out to be n times n plus 1 times 2n plus 1 all over 6. So I think of this as being related to the previous one, just has an extra copy of 2n plus 1 and an extra copy of 3 downstairs. It's like this thing times 2n plus 1 over 3. And the last one is the formula for the sum of cubes, which is also quite cute. This is going to be 1 cubed plus 2 cubed, or 8, plus 3 cubed, or 27. Second to last term being n minus 1 cubed, very last term being n cubed. This turns out to be the square of this, which is pretty cool. So you take n times n plus 1 over 2, that whole thing, and square it. Another fun task. See if you can show that the sum of I cubed is the square of the sum of I. All right, see if you can prove this using this. There's lots of good YouTube videos out there. There are geometric interpretations for these things. That's getting outside the scope of this course, but it would be a great topic for the math team. And if you guys are interested in doing some competitive mathematics, getting some prize money from competitions, some scholarship money from Santa Fe, making nice connections, people in the math and engineering communities here in Gainesville, come talk to me about the math team. If you're enjoying Calc 1 up to this point, you'd probably enjoy it. Okay, these formulas, those rules, definitions, why? Well, I want to approximate the area under a curve, and I want to do a good job at it. We're going to start with an approximation, and eventually we'll learn how to get the exact area out, but it is a bit of a process. So I want to just show you gently where this comes from, do an example or two, then show you how to generalize, do an example, then take a limit. I'm going to assume that f is continuous here, although it's not necessary to do so. We'll put A over here and B over here. This is the curve y equals f of x. The procedure goes like this. You take this interval from A to B and you chop it up into equal length subintervals. This is called a partition. We're partitioning the interval AB into n equal length subintervals. So maybe here's my first subinterval from here to here, my second subinterval from here to here, my third subinterval, my fourth subinterval, and we'll say fifth subintervals, pretending those are all equal length. A generally we call x0. This first point here where we chop is called x1. The second one is called x2, and you continue like this. And B is generally called xn. Here n is 6. And then there's two different ways I can construct a rectangle for each of these subintervals. What I'm going to do, I'm going to come to this subinterval, and I'm going to draw in here a rectangle whose height is determined by the height of the function. And I can do it like this, where the height comes from the left endpoint, or I could do it like this, where the height comes from the right endpoint. You see it? Right endpoint, left endpoint. Or I can look over here at this one. This would be right endpoint, left endpoint. I'm going to draw the, let's say, right endpoint Riemann sum first. Okay, so I come up here, the height is determined by the value of the function at that right endpoint. So here's the right side of my first rectangle. It is a rectangle, so it is flat on top. There she is. And this y value here, that's f of x1, right? It's the y value on the graph, y equals f of x, at the input x1. I do this for all the subintervals. So I take the right endpoint of each subinterval, extend it up to the graph, and let that determine the height of a rectangle. This would be f of x2. Take the right endpoint, come up to the graph, let that determine the height of my rectangle. Its height would be f of x3. And I do this for all of them. You notice that some of these rectangles are too big. They overestimate. Like over here, there's some area that's counted that's not under the curve, and some of them are too small. Now the widths should all be the same. The widths being different are just my bad drawing skills, but the heights are allowed to be different. I'm going to shade the area that we're trying to approximate. My art is bad. I don't feel too bad about it. Shading takes time. Art is hard. Blah, blah, blah. What I want to draw your attention to is that some of these rectangles are too big and some of them are too small. All right, the actual area that we're going to measure here is the area of the purple rectangles. The area I'm trying to get is the pencil shaded area, the area bounded by the curve. So what do I get with my approximation? One important thing I haven't told you is the length of each of these, right? What is the width of each of those subintervals? Well, we call this delta x. So each one of these widths is delta x. And since they're supposed to all be the same length, I take the total length of the interval AB and divide that by the number of rectangles. So the length of each subinterval, which is the width of each rectangle, is b minus a over n, and we call that delta x. The Riemann sum I just built for you is called Rn. And this is the sum of all the areas of the rectangles. And that sum would run from 1 to n. Right, like here, n was 6, and we have 6 rectangles. 1, 2, 3, 4, 5, 6. Yep. The first rectangle has height f of x1. The second rectangle has height f of x2, and so on. So the area of that first rectangle is f of x1, the height, times delta x, the width. The second one has height f of x2, and its width is also delta x. All of these widths are delta x. So we get here f of xi times delta x. Because this is the height of the ith rectangle. And this is the width.
I being the subscript, right?
Exactly. So if I write this out long form, like without the sigma notation, this would be f of x1 times delta x. That's the area of the first rectangle, plus f of x2 times delta x. That's the area of the second rectangle, plus f of x3 times delta x. That's the area of the third, right? Height of the first times width of the first. Height of the second times width of the second. Height of the third times width of the third. And this would go all the way out until we get to the last one. In the picture, it's 6. In general, it's just f of xn times delta x, right? Because the sum runs from 1 to n. This is called the right endpoint Riemann sum. You might guess from that there's also a left endpoint Riemann sum, and that is what it sounds like. It's where the height of the rectangles comes from the value of the function at the left endpoint instead of the right. There is also a thing called the midpoint Riemann sum. And then there's a much better form that uses trapezoids rather than rectangles, but we'll get there. Questions on the notation or where this is coming from, anything like that? Okay, if you're using left endpoints, we get the thing we call ln. And the easiest way to switch from right to left, this is not the same notation that every textbook uses, but just have the sum run from 0 to n-1 instead. Other places, they switch this I for an I-1. It's the same thing. There's always going to be n terms in the sum because there will be n rectangles. Here, that's going from 0 to n-1 instead of from 1 to n, because your left endpoint is determined by f of x0 rather than f of x1. So I will draw the picture for this as well, but first let me give you the expanded form, right? This is f of x0 times delta x plus f of x1 delta x, and on until you get to f of x sub n-1 times delta x. Maybe I won't draw the left endpoint picture in general. I'll draw a specific example. So let's get to some specific examples. We can kind of feel how this goes in practice. Formulas you need to remember: Rn is this, Ln is this. All right, so this formula you got to remember, and this formula you got to remember. The trick to these problems always, by the way, I should say, is to first calculate delta x. So let's do it. Let's take an example here. Approximate the area bounded by the squaring function f of x equals x squared, and the x-axis from x equals 0 to x equals 1 using, say, 5 rectangles and both L5 R5. So we'll do the left and right endpoints to try and approximate the area under this parabola, just between 0 and 1. I'm going to begin with a rough sketch of x squared on the interval 0 to 1. I'm going to zoom way in on quadrant 1. All right, whatever, I don't care what's going on over there. I'm going to call this right here 1. So here's the point 1, 1. The area that I'm trying to approximate, I'll shade in pencil. Of course, the challenge here is that these areas are bounded by curvy things. If they were made up of all straight pieces, then we can use like basic geometry. You can always break that down into things that you know how to calculate. When it comes to curves, areas become a little bit harder to find, right? Some special cases like circles and stuff we can work out, but here's the area I'm trying to calculate. if I chop the interval 0 to 5, sorry, 0 to 1 into 5 equal length pieces, delta x is always b minus a over n. So here that's 1 minus 0 over 5, or 1/5. Zero, of course, is right here. So if I chop this like 1/5, 2/5, 3/5, 4/5. There it is. There is my interval AB chopped into 5 equal length subintervals. Using the right endpoint Riemann sum, I can then draw in some triangles. Maybe I'll switch to black for these for contrast. Sorry, I say triangles, rectangles. Here's my first rectangle. Height is determined by the value of the function at this right endpoint. My second rectangle. My third rectangle. Fourth rectangle. And my fifth rectangle. I think it's pretty clear that this is going to be an overestimate, right? The area of the rectangles is definitely larger than the area shaded by pencil, because the pencil shaded area fits entirely inside the rectangles. R5 should be the sum from I equals 1 to 5 f of xi times delta x. And you can compute the xi's as you saw me do here really quickly. The formula for the xi's, if you want it, and we will need this from time to time, is a plus I times delta x. In fact, I would say if you, let's see, where did I suppose? Back here. Let's get this on the same page. Xi is a plus I delta x. So you need this, you need this, and two summation formulae down here, Rn and Ln. So take a second, we're casual today and all nice and gentle. Go back to the part where you have your Rn and Ln formulas in your notes and make sure you've got both of these. For now, the xi's, when we've got a finite number of them, we can always just figure out what those numbers are. But down the road, we will need this more general formula for the xi's. The idea being to get to like the fourth endpoint, you start over here at A and you walk 1 delta x, 2 delta x, 3 delta x, 4 delta x. So to get to the ith endpoint, you start at A and walk I copies of delta x to the right. Okay, coming back to our computation. So again, A is 0. Delta x was 1/5. So this is I times 1/5. And that's where these numbers are coming from, right? 1/5, 2/5, 3/5, 4/5, and 5/5 is 1. All right. So I now plug this into my formula here. This should be f of x1 delta x plus f of x2 delta x. I'll just write out to f of x5 delta x. We can do the computation without doing these two symbolic steps, but I'm going to do these symbolic steps to kind of prepare us for the later stuff. F of x1, well, f of x is x squared, right? That's the function we're working with here. And x1 is 1/5. So this is 1/5 squared times delta x, which was 1/5, plus f of x2, well, x2 is 2/5. The height of this rectangle, therefore, is 2/5 squared. That's f of x2, 2/5 squared, and delta x is still just 1/5. The next term would be f of x3 times delta x. F of x3 is x3 squared, or 3/5 squared. Then f of x4, x4 was 4/5, so that's 4/5 squared times this delta x, which is 1/5. And then f of x5 is 1 squared, so 1 squared times 1/5. A neat fact, of course, you can factor out the 1/5, right? 1/5, 1/5, 1/5, 1/5, 1/5. So I'll have 1/25, like big parentheses here, 1/25, and then 4/25, and then 9/25, and then 16/25, and then 1, all times 1/5. So I factor out the 1/5 that's in each of those, and then each of the squares, 1/5 squared, 2/5 squared, 3/5 squared, 4/5 squared, 5/5 squared. I simplify those just a little bit. So this 1/25, that's the 1/5 squared. The 4/25, that's the 2/5 squared. 9/25, that's 3/5 squared, and so on. This sum, I don't have the patience for myself. We could, of course, compute it as a sum of squares. You could factor out the 1/25, but for my money, just use a calculator at this point. No harm in that. Plus 9/2 plus 16/2 plus 1. We get 2.2 times 1/5. I'll write that down. And then if I multiply this whole apparatus by 1/5, we get 0.44. So here it all is. This window, lighting. There it is. So that pencil shaded area there, that's approximately 0.44 units of area. We said it earlier, is this an overestimate or an underestimate? Is the actual area smaller or larger?
Smaller.
Smaller, right? These rectangles are counting lots of area, like all this stuff. that they shouldn't be counting. Let's do the left-hand Riemann sum. L5. We know this is the sum from I equals 0 to n minus 1, so the sum from 0 to 4 of the same thing, f of xi times delta x. So that's going to be f of x0 delta x plus f of x1 delta x. It's a lot of the same stuff, f of x2 delta x plus f of x3 delta x plus f of x4 delta x. x0 is 0, f of x is x squared, delta x is 1/5. So this is 0 squared times 1/5 plus 1/5 squared times 1/5 plus x2 is 2/5, so that's 2/5 squared times 1/5. x3 is 3/5, so that's 3/5 squared times 1/5, and 4/5 squared times 1/5. So again, factoring out the 1/5, we get 0 plus 1/25 plus 4/25 plus 9/25 plus 16/25 all times 1/5. And again, no shame in using a calculator for the arithmetic at this stage. I certainly will. So that's a 0 here, and get rid of the 1 here. And I'll do it without the 1/5 at the end with the 1/5. So this is going to be 1.2 times 1/5. And then if we slap on that delta x, we get 0.24. So here's the computation for L5. And we said earlier that this is an overestimate. This is going to be an underestimate. And you can see it from the picture. The left endpoints are going to underestimate the area. Because that first rectangle now has height 0, right? Down shade the area, blah, blah, blah. So that first rectangle now has height 0 coming from the value of the function at the left and point to the first subinterval. So this first one now is just like this, no height at all. The second one now is like this. The third one, like this. Fourth one, like this. And the fifth one, like this. So again, this time you see the rectangles come up short. There's lots of pencil shaded area that isn't measured by the rectangles. And that's how we know that this is an underestimate. The actual area there. So let's give some conclusions. So we deduce that the exact area bounded by f of x equals x squared on the interval 0 to 1 is between 0 point, was it 24 and 0.44. Now, a fun question is, how can we find that exact area? Or maybe a gentler question, how can we improve our approximation? And there are a bunch of good answers to this. So I'd love to hear your thoughts. Does anybody have an idea how I could get a better approximation for the exact area under this curve? Guesses are fine. Any thoughts at all? Imagine you're the only mathematician out there thinking about this stuff.
Okay, this is a simple one. My mind just said to add them up and divide it by 2.
That's an awesome one. Yeah, average Rn and Ln. This gives you something special. It's called Tn. If you know one's an overestimate and the other one's an underestimate, then the average of the two is probably getting better, right? The reason we call this Tn is because it gives something called the trapezoid rule. That was the rule I mentioned a minute ago. If you know the formula for the area of a trapezoid, it is literally the width times the average of the two heights. So what this would give us is the area that you get from kind of these super simple trapezoids. Let me draw a more extreme curvy thing here so you can see it. A, B, chop, 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 chop. So if you take the two endpoints both together and you just connect them with a straight line, this turns out to be the same thing as averaging the left endpoints and right endpoints. And this does a phenomenal job. Right, you can see how those black trapezoids would come very, very close to giving the right answer. Well, maybe a slight overestimate in some cases or a slight underestimate in others, but it's going to be extremely close. So close, in fact, that I'm having a hard time drawing the error portions here. So that's a wonderful answer. Yeah, average the two. There are other ways, though. Any other ideas?
Instead of right or left, go from the center.
We could take our sample points to, yeah, come from the middle. So using the midpoint, how much this helps kind of depends on the sort of function you're dealing with. For a monotone function like x squared that we were doing a second ago, it does a lot of good. So I take my height to come from the center of each of these subintervals instead. So here's my first rectangle. It'll look like this. Second rectangle would look like this. My third rectangle look like this. And my final rectangle in this picture would look like this. So the midpoint approximation, again, for monotone functions, for functions that are always increasing or always decreasing, will lie between the left and right endpoints. We'll give you an answer that is in between those two answers. But for more general functions, it doesn't necessarily produce an improvement. Let me shade here again the area we're trying to approximate so we can see what's going on. So you see here, the midpoint rule misses a little bit and then goes over a little bit. Here misses a little bit and goes over a little bit on that side again. Here I miss a little bit on this side. And then it's hard to see, but I go over a bit on that side. Over here I miss a little bit on that side. And under a little bit on that side. So all of these are good ideas. The trapezoid rule, just from the picture, kind of looks the most convincing. Here I've got a little bit missing, a little bit missing, a little bit missed. Midpoints are also good. The thing you need to modify to get the midpoint is you change xi. We can call it, you can use xi star, and this is the midpoint between xi and xi plus 1, which is xi plus xi plus 1 over 2. So you kind of average the sample points rather than averaging the heights. So this would be like x1 star, this would be x2 star, x3 star, and x4 star. And then your midpoint rule can just be expressed as mn equals sigma. I guess here we'd have to start at 0 using the way I wrote it there. 0 to n minus 1 f of xi star times delta x. I'm not a big fan of the midpoint because it's just a bit of a hassle, right? You have to go through and calculate the midpoint of each of your subintervals, and it can be a kind of a pain. There's one suggestion that nobody's mentioned yet, and it's kind of the obvious one.
Increase the number of rectangles.
More rectangles, right? In the example we just did, I used 5 rectangles for the left, 5 rectangles for the right. If I use like 1,000,000 rectangles, then that shit's going to get way closer. And that's sort of the easiest thing to do. Let me show you. All right, 3 rectangles. Okay, 4 rectangles. Okay. Maybe like a dickload of rectangles. How about that? How about like so many rectangles that you can barely see them? You see how the rectangular area here is going to be a lot closer to the actual area than the rectangular area here. just by piling in more and more and more of them, making them smaller and smaller and smaller, the estimate becomes more sensitive to changes in the height. So more rectangles is sort of the obvious thing. And that's how we're going to get our exact area. So continuing that bulleted list, improve, approximation, continued. Last thing is more rectangles. Now, if 10 is better than 5, and 100 is better than 10, and 1,000,000 is better than 100, infinity should be real fucking good. And it is. That's going to be the game. So as n gets bigger and bigger, both Rn and Ln get closer and closer to the exact area. So does Tn and so does Mn. All of these Riemann sums get closer and closer to the exact area as you use more and more rectangles. But Rn is kind of the easiest one to work with. So in fact, this brings us to something of a definition. If f is a positive continuous function on the interval AB, then the exact area bounded by f and the x-axis is the limit as n goes to infinity of Rn. That's usually the way we say it. You could use Ln here, you could use Mn here, you could use Tn here, but generally we use Rn because it's the easy one to work with. And this is the limit as n goes to infinity of the sum from I equals 1 to n, f of xi times delta x, where delta x is your b minus a over n, and xi is a plus I delta x. Now we are out of time for today, so I won't be able to do the calculation for you here. But next time we will calculate the exact area underneath x squared from 0 to 1. It's going to be 1/3. And I will begin introducing more notation and definitions, stuff like that for you. All right, so we're going to pause here for today. Next time I'll do a calculation of exact area using this, this fact. And we'll look at some application problems where the function f is something from physics like velocity, and we'll get something out like distance. So we'll talk about units and exact values next time. Any questions from you before I wrap up here? Yes.
Yes.
Go ahead, Jeff.
So the problem we did before, I was just curious on how did you get to where fx was going to be squared?
Oh, because the function we were playing with there was the squaring function. So kind of right at the start,
okay.
They told us, you know, we're going to approximate the area bounded by f of x equals x squared.
Oh, that's right.
Yep. Yeah, so once you get to kind of this stage where you've got your delta x, you know your xi's, and you got to plug in, just go back and look at what function you're trying to find the area under. Other questions before we wrap up? I see your message, Evan. We can hang around. Okay, then that is it. I will see you guys on Wednesday. I am going to put up a homework for you on WebAssign. So please do take a look at that and try to solve at least a couple problems between now and class on Wednesday. Otherwise, I'll see you then when we get to whip this thing out for the first time. Take care, guys. Alrighty, Evan, what's up?
Hey there. So can you hear me?
Mm-hmm.
All right. So I just I finished up the makeup exam earlier, and I had one question about